Hello, everyone. My name is Jordan. I'm an undergraduate research student under Professor Jeff Lundeen. This project was done in collaboration with Professor Boyd, where I worked closely alongside Dr. Orad Reshef. So imaging systems can be quite long, even inconveniently long at times. So how can we make them shorter? One possibility is to use metal lenses. Metal lenses can be used to replace the relatively thick glass of classical lenses with a much thinner optic. But as you can see, that leaves the spacing between the lenses unaddressed. And so what we propose is to use a device we've invented called a spaceplate. A spaceplate can be inserted either before, in between, or after optical elements to decrease the size of imaging systems even further. This could lead to getting rid of the camera bump on the back of your phone, for instance, or making thin film telescopes and microscopes. To understand in more detail how such a device works, let's consider a single ray propagating through free space. So here are rays propagating over a distance d effective in the z direction and over a distance w in the x direction. What we want a spaceplate to do is to compress this distance d effective into a much shorter distance, here labeled d, all the while conserving the propagation distance w in the x direction. We define the compression factor, r, as being the ratio in between the distance that the ray appears to have traveled over the distance that the ray has actually traveled, i.e. d, the thickness of the spaceplate. If you have a compression factor of 1, you're essentially propagating through free space. But if you have a compression factor of, say, 6, you've just inserted 6 times as much propagation into your system. This is very different from how a lens or even a metal lens works. A spaceplate changes the position of a ray, but the direction is conserved, whereas a lens will change the direction of a ray, but the position is conserved. Or said differently, a spaceplate changes the position as a function of angle of an incident ray, whereas a lens changes the angle as a function of incident position. And if you were to insert a spaceplate into an imaging system, you would have the effect of moving the focal plane closer to the object being imaged. So how do you make a spaceplate, and is it even possible to make one? These are two questions that our group set out to answer. And the first possibility we came up with was to use a low index medium. This works exactly as the name suggests. You find a medium with an index lower than that of the surrounding environment. The other possibility we came up with was to use a uniaxial medium, and this one works by using birefringent walk-off. So our group came up with these two possibilities and tested them both in the lab. And surprise, surprise, they both work. Now, as exciting as this may seem, the compression factors that they found were quite low, i.e. 1.48 and 1.12, respectively. I'll remind you that a compression factor of 1 means you're propagating through free space, so there might as well be nothing there. The higher the compression factor, the more performant the spaceplate. So this pushed our group to come up with other ways of making high compression spaceplates. And what we came up with was to use non-local metamaterials. And making such a spaceplate is the topic of my talk. So how do you design a spaceplate? If you wanted to make a lens, you would build a device that changes the phase as a function of position. But as we already saw, a spaceplate doesn't do that. So here I put the equation describing the output phase of a spaceplate. And you can see its variables are the index of the background medium it's replacing, the distance the ray appears to have traveled, the incident angle, as well as the operating wavelength. And when you plot that, you get something that looks like this. And so now we have something we can aim for in our simulations. Our group's first attempt was to use a genetic algorithm. And so here is the actual structure that the algorithm found. It's a bi-material multilayer stack using silicon and silica. The compression factor of this device is just under 5, which is almost 4 times as high as anything that was observed in the lab. And this device only works with incident angles of light between 0 and 15 degrees, and that is by design. This corresponds to a numerical aperture of 0.26, which is the point at which devices like this would begin to have applications in industry. And the operating wavelength of this device is 1550 nanometers. Now here's the output phase of this device. And as you can see, up until 15 degrees, we have this remarkable fit between what we would expect to see and what we actually observe. The one shortcoming of this particular device is that it has a poor transmission, i.e. it has 6 dBs of loss at 10 degrees, which is the peak transmission. However, this device is polarization independent, and when we run it through a full wave simulation, we see that we get just about 50 microns of propagation in 10 microns of spaceplate. Now, before I keep going, since we presented at Clio in 2020 and posted our manuscript, other groups have proposed other methods for designing spaceplates. Notably, the Shenhui Fan group proposed using photonic crystals, and the Matikoni group brought forth the idea of using coupled cavities. While working on the genetic algorithm approach, people from outside the group recommend that we try using a gradient descent algorithm. Now, there were many different optimization schemes that we ended up trying, but the one we stuck with, one of the two that we ended up sticking with, goes something like this. Our code takes a target compression factor and then generates a swarm of multi-layer stacks with random layer thicknesses. Now, when you're optimizing a multi-layer stack, you can either be changing the thickness of each layer or the index of each layer. And for this first method, we were optimizing the thicknesses of each layer. And so then our code would apply gradient descent to the thickness of each layer. We would then use the transfer matrix method to get the phase and the transmission of each stack, and then compare that, i.e. fit that to the expected phase we would see if this particular device had the target compression factor. We would then calculate the root mean squared error between the two, and our figure of merit was to decrease this error. At first, when we got the code working, we were blindly exploring our parameter space, and we weren't gleaning much out of that. And so we created a data set of space plates with different parameters. So we explored 5 different ranges of incident angles of light. We changed the number of layers of 9 up to 29, and explored target compression factor values of 2 and above. That study yielded many different space plates. And for an apples to apples comparison, here's the best one that we found with the same numerical aperture as the one generated with the genetic algorithm. And so first off, this one has 21 layers, whereas the genetic algorithm spaceplate had 25. And this spaceplate happens to be 5 times thinner. But where things begin to get more interesting is here. By switching over to a gradient descent scheme, we were able to more than double our compression factor. And we even saw an improvement in our transmission. However, the one thing that we had to give up to get all these improvements is that our spaceplate is no longer polarization independent. Now, you might be looking at the output phase of this particular device and looking at the fit, thinking visually, it's not a very good fit. So how do we know that the spaceplate isn't just introducing a lot of aberrations into our system? And that is where the Strel ratio comes in. The Strel ratio is simply a number between 0 and 1 that indicates how aberrated an optical system is. If you have a Strel ratio of 1, your system is unaberrated, but anything above 0.8 is considered to be diffraction limited. Now, I'll be presenting the data that we got for all 17 layered devices, but know that this graph is fairly representative of the data that we got with devices of any number of layers between 9 to 29. And so here on the x-axis, we have our targeted compression factor, and here on the y-axis, we have our Strel ratio. So the first thing that I want you to notice is that every single one of our devices is well above the diffraction limit of 0.8 down here. The other thing I want to point out is that as we increase our numerical aperture, we have a decrease in our Strel ratio, i.e. the amount of aberrations introduced to the system increases. So there's this trade-off here between numerical aperture and aberration. There's also another trade-off that we observed in our data between the numerical aperture and the compression factor. And so here is the same device that I was showing you earlier, but now what I want to show is that by decreasing the operating range of incident angles of light, I can increase our compression factor. And so instead of having a device that works between 0 and 15 degrees, we have one that works between 0 and 10, and all of a sudden we almost doubled our compression factor. And in the process, we even saw a slight increase in our Strel ratio. And as I said, we were able to see this trade-off across all the data that we took. So here we have our numerical aperture on the x-axis and the achieved compression factor. So not the target one, the one that we actually managed to get on the y-axis. And it's very plain to see that as our numerical aperture increases, the achieved compression factor decreases. Now there is one more device from this study that I would like to present, and it's the one right here. So compared to the ones shown previously, this one has 27 layers and only works between 0 and 1 degrees of incident angles. And by having such a low numerical aperture, we were able to achieve a compression factor of almost 340, which is a record for that numerical aperture. And this particular space plate introduces next to no aberration at all into the system. Now, earlier in the talk, I mentioned that there were 2 different methods that we explored for generating space plates, And the first one that we used was to change the thicknesses of each layers while leaving the index of each layer the same. But the second method that we tried was to set each layer to 5 nanometers in thickness and then attribute each layer with a random index and apply gradient descent to the index of each layer. Everything else in the method stayed the same. So here we have a device with 100 layers of 5 nanometers, and we were able to achieve a compression factor of 6.4 by limiting it to somewhat realistic materials, i.e. between 1 and 4, an index of refraction between 1 and 4. And now you might be thinking, well, this isn't a very high compression factor. Earlier, I showed you a device that had a compression factor of 20 for the same numerical aperture. But keep in mind that this device is only half a micron thick, whereas the ones showed previously were several microns thick. And now we wanted to know, well, what would happen if we allowed it to use any material with a positive index of refraction? And just by playing around with the code a little bit, we were able to get a compression factor of 80 in only a 0.5 micron thick device. Now, as you can see from our color bar, this device isn't necessarily fabricatable because it uses materials that don't necessarily exist. But what this does tell us is that the performance of a spaceplate likely depends on the index contrast between the materials. So in conclusion, a spaceplate is a device that can mimic a compression of free space. We were able to generate spaceplates with a wide range of compression factors and varying numerical apertures. And we observed two trade-offs, one between how high of a compression factor we could get and the quality of the fit, i.e. the amount of aberration introduced into the system, as well as between the numerical aperture and the quality of the fit. And just by switching over to a gradient descent method, we were able to improve our transmission of our devices. Thank you.